Good morning, everyone. Good morning, Azra. Good morning, Homer. Hi, Hike. Hi, Downey. Hi, Charlie. Hi, Rainy. So, I'm in period D today. Guess that's just Charlie and Downey. Due today, scratching the surface before midnight. Hopefully, we only have those 3 evaluates. Maybe you have a couple questions on part of the extend. We'll go over the extend section today. We'll finish the evaluate. Alright. No, it's not baby. My mic cut out randomly again, like it did yesterday, so I had to try and fix that so you can hear me. Otherwise, this whole thing would be pointless. So like I was saying, we'll finish up scratching the surface today. Okay? Review the extend section, answer the evaluate questions, and then submit the document in Google Classroom. Virtual Classroom gives you the agenda. Fun fact though, and kind of leads into reviewing the extend section, some sources, this comes from a college in Brooklyn, some sources state that in the North Atlantic, the rate of movement between the North American plate and then other plates around it, the separation is about 1 centimeter, about half an inch per year, while in the Pacific, it's about 2 inches every year. And then other people, the sources say, in general, they travel about 5 to 10 centimeters a year. So, it seems the North Atlantic, the North American plate, a little slower. The Pacific's a little faster than the North American plate, but then the rest of the plates move a lot. And so, the entire surface of the Earth is like a broken eggshell. It's a crust. And it's very thin and brittle because it's made out of very low dense minerals and rocks compared to metal. And even the sea floor is considered part of the crust. Okay, that's not the mantle. So the sea floor, as deep as you can go, that's still part of the crust. Just to show you how deep these layers go, right? So the entire Pacific Ocean is sea floor. North American plate has half the Atlantic Ocean and then the rest of North America. Alright? And so these plates shift on top of the mantle. Their direction is determined by where you have convection currents happening in the mantle. Right? Kind of hoping what I was hoping you were starting to see yesterday. So you kind of look for areas where the plates are separating. Here, here, here. That's all along the Atlantic Ocean, right? separation here, here. These are all dividing boundaries. These are all divergent boundaries. So what can we assume is happening underneath the crust here? That there is a convection current where two upwelling currents are matching together. And that's like what you'd have seen in scratching the surface in the first question of the extend, is when you hold down the adding thermal energy, you're going to create a current that's going to push the rest of the mantle to the side. So just quickly go back here. You just keep holding down this. You are aligning basically multiple upwellings, and that's a dividing boundary. See how it's going to the sides? That's a divergent boundary. That's what is circled on this map. I just picked out a few examples. So underneath, you have two upwelling currents, part of convection cycles in the mantle, where you have a convergent boundary, so the two plates kind of colliding. So let's change up the color. Where you have a collision, all along here is a collision, all along there is convergent. So the whole western side of the Pacific Plate is a convergent boundary. It's kind of cut off, but you have the Indo-Australian plate converging. And this is where you're going to see mountains, right? Even along right here, the Nazca plate is colliding into the South American plate. You have the Andes Mountains there. You have the Himalayan mountains there. You have, the whole archipelago of Japan right there. Japan is rising seafloor. So the geological features that we see across the Earth come from these plates colliding, separating, moving across each other. Why are they moving, colliding, and separating across from each other? Is because of the action in this largest layer of the Earth. And so, just like the second question, how do you get a convergent boundary? You just add cold. But we know cold doesn't exist, so we take thermal energy away. And now, on either side of this black line, where there's lack of thermal energy and sinking material down to the core, the mantle's moving in, it's converging and sinking down. And that's where you get convergent boundaries. There's a third type of boundary in plate tectonics, and it's a transform boundary, and you see these where two plates are kind of slipping past each other. Don't really mark it here on the map, but in Southern California, the San Andreas Fault, the boundary between the Pacific Plate and North American Plate, is famous for producing very strong earthquakes in the United States. Other transform boundaries, they don't really mark them very well. Probably have some right there across the Mediterranean. Few more out in the Pacific. Okay, so there's multiple types of boundaries between all these plates. The entire surface of the Earth is the crust, even the ocean floors. Alright? So that was the fun fact. And they're very slow moving, so this whole movement of the plates takes a long time. Plates that collide, the denser plate will sink under it and called subduction. So the Pacific Plate is denser than the Eurasian Plate. So if we go back here, the Pacific Plate is denser than the Eurasian Plate. This Pacific Plate will sink under the Eurasian Plate and push up the edge of the Eurasian Plate. And that's how you get the archipelago, the island chain of Japan. Marianas Trench is in here because the Pacific Plate is sinking down. This is where you get a lot of trenches. You'll get seamounts, make islands, right? Lots of volcanoes, very volcanic area. You know, the whole border of the Pacific Plate is called the Ring of Fire because there's a lot of volcanoes. Very geologically active. Hawaii is a little bit of an anomaly right there, because it's right in the middle of a plate, yet we know there's lots of volcanoes and it's an island formed by volcanoes. Well, we call that a hot spot. For some reason, there is a forming, upwelling in the mantle that is kind of punching a hole through a weak part of the crust, and that volcanism makes a new island. Not so dissimilar from the supposed supervolcano that's in Yellowstone National Park, right? Hot spot underneath the North American plate. So 5, what happens to the surrounding currents? Well, they will start to divide, move away. The cooler sinking currents will then collect on the other side of the planet. 6, what happens to the surrounding currents when you start to take away thermal energy? They're going to start to converge, and the opposite side of the planet, the upwellings will happen more frequently. So, my little fun fact kind of goes into 5 and 6. 7, can you ever make the entire model reach equilibrium and stop convection? Probably close out of that. Refresh it so I have something blank to work off of. If I pause it with backspace, and let's see, yesterday I tried to add in thermal energy. What if I remove it? Alright, well what if I try and add it? Definitely got warmer, but did convection stop? It slowed until it no longer doesn't. Now it's back to basically looks like normal. So, can you ever reach equilibrium? No, because there's two different sources of energy, or lack of energy on the crust, this black, and this white hot core. To reach equilibrium, you would have to make the core and the crust reach the same temperature. Will you ever be able to do that? No, because the deeper you go, the higher pressure is, and the more greater the temperature is. So greater depth, greater pressure, greater temperature, you'll never reach equilibrium because it always gets hotter as you go down. When you have a difference in temperature, you get a convection current, right? Difference in density, difference in temperature. High goes to low, high thermal energy to low thermal energy. So no. Then 8, 9, 10, and 11, oh, it's just 10, these last 3, talking about earthquakes. You can use this simulator to show an earthquake. Let's look at seismic waves. You hit the space bar. I have a seismograph. I have its readings here in the core just so I can see it, because I can't see it in the black outer space or the black core. Wherever I click, I create an earthquake. So if I hit it close to the seismograph, very strong amplitude initially, and then it weakens over time. Some of the waves reflect off the outer core back to the seismograph, and they get picked up a second time. And that's what these blips are right here. But the rest of the seismic waves will all ripple throughout the entire mantle. So there's always earthquakes happening, not super strong ones that will destroy human civilization on the surface, on the crust, but this mantle is always rippling due to different bumpings and movings of the crust and shifting of the rock that's convecting, because it's not 100% magma, it's moving rock, convecting rock, very slow. On a geological time scale for humans, very slow. Right? If you put it on the opposite side, so that's question 8, describe the activity over time. Now go on the opposite side of the Earth. Give it more time. Will you see seismic waves from an earthquake on the other side of the Earth? It's bouncing, reflecting around the outer core. Some of them goes through the outer core. Eventually, they'll converge, and they'll get picked up on the seismograph. So little earthquakes are happening all the time throughout the mantle. So there's always these ripples, and you can try and measure really strong ripples and time when the earthquake happens to the strength and the timing of when they reach certain locations, and you can determine that, hey, some of these waves should be going through the outer core, should be going through the center of the Earth, but they don't because of the density, the high metal content of the outer core. They never reach through the outer core. It's a different density. They can't ripple through it, so they go around it or they reflect off of it. And now you as a scientist has discovered that, hey, that there's a core in the Earth. And you can start to determine based on the reflections and the speed that that material is a certain density, and then you can relate density to the elements in the periodic table, because density is a characteristic property. It gives it an identity. And we find out there's a lot of iron and nickel in the outer core. So 8, to describe the activity over time. Strong initial waves dissipate over time as it moves through the mantle. Describe the activity over time. When you go on the opposite side, it takes a while for the seismic waves to reach the seismograph, but eventually they do. Not as strong as if they were right next to the seismograph, but they are picked up on the opposite side of the Earth. Do seismic waves travel through the core? No, they don't, because the core has a different density than the mantle. You need a lot of energy if you're going to ripple through liquid metal. So that brings us here to the evaluate. 11. How does density and pressure affect the composition and state of matter of the Earth? Refer back to your explain answers. We talked about density and pressure. As depth increases, there is a greater pressure. That's going to turn the outer core into a liquid because of the intense heat, but then turn the inner core into a solid because the atoms no longer have anywhere else to move. They cannot become a liquid, right? The composition, because the Earth's layers separate based on density. So the composition is based on density. The state of matter is based on pressure. Denser elements and materials will go to the center of the Earth. The mantle is semi-molten. The outer core is liquid. Inner core is solid. The crust is solid because it's the coldest layer. But silicon, oxygen, magnesium, they are incredibly less dense than the other materials. So picture the crust is kind of like styrofoam floating on the mantle, floating on water, even though the mantle isn't entirely liquid. Just that's how we kind of think about it. That's not an answer. You have to build off of this.
I could stay like this, forever following you. Just don't get too far.
Any questions so far? Why are there convection currents in the mantle of the Earth? Again, you can't have the mantle reach equilibrium because there's a difference in temperature. So, explain how pressure causes differences in temperature. Temperature versus depth, positive relationship. Increase the depth, you increase the temperature. Right? So the core and the crust have differences in temperature. When you have differences in temperature, you're going to create a convection current. You're going to create movement of matter. We've been talking about that whole year. Convection at the beginning of the year, wind, ocean currents, climate change. Not so much in space, but now back here to the Earth in the mantle. What effect could convection currents at a line in the mantle cause on the Earth's weak crust? If the Earth's crust is brittle, low density, it can break based on the currents. And so we can call these pieces tectonic plates. Use the map from today's fun fact, right here. This one, again, right? So there's all types of plates. Why are they moving? Are they aligning upwellings? And are they dividing? Is it a divergent boundary? Or are they colliding? Are they converging, a convergent boundary? What's happening underneath the boundary? Is it sinking or rising? So use, obviously, the extend section. So, I mean, that's pretty much the document. I reviewed the questions, kind of gave you some guidance. If you guys have questions yourself, I'll gladly answer them. But this document is due today before midnight. So when you are done, you turn that in. Anybody done in period D? 4 of you. If you have any questions while you're working on it, you know, throw that in chat or send it through email or remind. This is going to be your last, pretty much big assignment in science anyway. Next week, tomorrow's a quote-unquote AC Lab day. So any revisions or missing work for any class. Next week, Monday, June 1st, is a teacher PD day. And then they haven't really said what they're doing, but the idea is that whole week is for students to catch up if they are missing work. I know you guys in chat or listening are pretty accountable and get things done, but there's a significant portion, not the majority, but there's a large portion that they want to give more time to. How much longer of this distended distance learning? Distance learning is done for the whole year, which ends officially June 12th, but these last couple weeks, these weeks in June, are going to be more of catching up, doing team activities. So we're going to kind of be doing, mighty meetup kind of stuff. Pretty much in June, the last week, maybe next week, depends on what teachers want to do. And then it's up in the air what happens to start next year. Anthony Fauci, Dr. Fauci, is the kind of like the leading health expert in the country. He was optimistic that there's going to be a vaccine end of the year. That's good. He's hoping that if everybody keeps following these guidelines the states puts out for reopening and for distancing still, that there won't be a second wave. So no second wave and a vaccine. It's a pretty positive start to the new year, so 2021. But who knows what September looks like. Different people are talking about alternating days. Some students go in, some students stay home, just stay online, forget it, and just come in. Different states are doing different things. So remains to be seen. Cool isn't a thing. Neither is chill. Just go back to school. Well, the problem is kids are really good vectors. They carry disease really well. And while you guys aren't really affected, your parents, teachers, grandparents can be affected. Hoping school will be normal next year. If not, that would be a weird transition to high school. Yeah, it would be. You would have to listen to teachers you haven't really met or seen in a new atmosphere. It's high school, but it's not really a high school. You wouldn't really be able to interact with other peers, classmates, unless teachers made certain projects. Projects are tough because you need materials. Unless maybe you're doing research like social studies, ELA. Yeah, it's not cool. It's not great. Be awkward when we do come back and see what they look like. I've had the same thoughts. It'd be like, how am I going to teach students I haven't actually met in person? This distance learning, kind of sucked. But at least I knew you guys and we could just transition to going offline. Starting brand new, I mean, you guys feel it'd be awkward. Teachers would feel it'd be awkward. Brand new students, how would that work? Homer won Mike Gets Pet of the Day. I didn't know Mike did a Pet of the Day. Cute. Was Homer the only entry? They should make a VR school program. You code that. You talk to Musk. You're gonna do that, or Valve. Steam. For number 1 in the explain, do we have to answer it like the last explain section question? For number 1 in the explain, what is pressure? What are 2 ways to increase it? So we have to answer it like the last explain section question. So do you have to answer 1 as number 4? Pressure and 2 ways to increase it, and how that relates to number 4. I meant the evaluate. So number 1, what is pressure? What are 2 ways to increase it? And then down here, what effect could convection currents that align the mantle cause in the Earth's weak crust? I mean, just defining pressure and discussing it, that was just to help you get the idea of what pressure is. It wasn't meant to have you explain what's going on. I want you to kind of explain very limitedly, why is the Earth's crust broken up into pieces, and why do the pieces shift around? Why does that happen? And you can talk about pressure because that's going to generate heat in the core, but it's the heat in the core in the cold crust that's going to cause convection in the mantle, and the convection currents in the mantle are going to move those pieces around. Some of the convection currents are going to be sinking and cause the plates to collide. Some of the convection currents are going to be rising and cause the plates to separate, to divide, divergent boundary. Downey, what? Keep switching on me. The last question in the explain and the first in the evaluate. The last question in the explain, how does density affect composition? And the first in the evaluate. You can use that to build off of it. So density, how does it affect the layers? Yes, you can use that answer to answer this part right here. Okay? Are we clear? You can use the number 4 as part of your answer in number 11. Okay? And you can probably use number 3 for the other part. So if you put 3 and 4 together, you're going to get number 11. Alright? Here, how about this? So you can see it. You guys don't need to see the comments, but use answer to number 4 to help explain. Use your answer to number 3 to help you explain. There. Alright. Let's just take class on VR chat. Yeah, because VR chat has nothing bad on it, or is not distracting at all. Plus, everybody's got a VR headset and has access to it, right, Ryan? Yes, of course. So again, if you have questions, let me know, but kind of taking a tangent. This is Raito's website. Kind of gives you the total counts of things. This is what I like to, take a look at every now and then. Rhode Island daily COVID-19 counts. You can see that exponential growth right here. And then it just kind of stops and then drops. Slowly though. You can see that like each peak almost linearly. It's an exponential increase and then a slow linear decrease. So yesterday, the 26th. Oh, that hasn't really updated it. 25th, 26th. Where's the 27th? But you have low numbers, you have high numbers. That's hospitalizations. Where are most of the infections? They didn't put 27th data in there. Interesting. But this is good as long as we maintain. Still distance. Social distancing within reason. PlayStation VR. Now everybody's got a PS4. Me too, Azura. I missed it before, but there were probably more. You're not certain that there were more in the entries. And he's a skater, so Homer rides a skateboard. Well, I was referring to Nikolai. Nikolai said PS VR. Xbox doesn't even have anything VR, do they? Well, they had HoloLens. I don't know if they actually released that or not. Bye, Nikolai. You got a board and he loves it. Wonderful. Logan's got both. I want you guys to know that. I said not everyone has one. Mr. Keynot. You can have two? You can have both or two? Or are you referring to PlayStation 2? Nice. You're very invested into the Xbox brand. I feel like my generation was invested in the Xbox because of Halo. But then it kind of shifted to PlayStation as I got old. Very interesting to see. Rainy's got it all. That's good, Ryan. Switches are cool. That thing was big and heavy. The original Xbox Azura. Getting ghosts. Bye, Downey. I might be using my Switch next week to at least do something fun, but then also something about geology. Maybe using, and everyone plays it, but Legends of Zelda to talk about plate tectonics. See how that works. I didn't know Roblox was an exclusive. I'm confused on number 12. 12. Why are there convection currents in the mantle of the Earth? Explain how pressure causes differences in temperature versus depth. So I want you to tell me why are there convection currents to begin with, Rainy. Convection requires a cycle. Convection requires a differences in temperature. You can't get a cycle or a current because the outer core is much hotter than the crust. So thermal energy must transfer from the core to the crust because these swirls here are actually solid rock. These rocks are going to become less dense as they heat up, rise, and move up, and then cool at the crust and sink back down. So, well, part of the molten part of the mantle will be doing that. It's like the treads of a bulldozer a little bit. The little wheels in the bulldozer, they're spinning, but they move the tread of the bulldozer around. The tread would be the crust, the wheels would be the convection currents. Like if I don't know why if caps is on. I don't know, this is just kind of how I think about it, right? So the tread of a bulldozer is kind of like the crust, and then these little wheels are like the convection currents, and they move the tread. So inside the mantle, these convection currents are turning, and when they align, they push plates apart, and when they sink down together, they pull plates together. Convergent and divergent boundaries. That kind of more for number 13, but I just want you to understand that there's convection currents. So let's going back to convection. Define convection, Jacob. Use your key term guide if you need to. Define convection, and then relate it to the mantle. The deeper you go, the hotter it is. So the heat transfers to the crust. Okay? Hike wants to know how Zelda is related to plate tectonics. It's because in Breath of the Wild, Hyrule has active geology. And specific geological land features. "13 is kinda like earthquakes. It's just an extension of number 12. When the plates collide or bump into each other, they will create earthquakes. So it's the movement of the plates that will cause these earthquakes. Pieces of broken crust are called tectonic plates. These are tectonic plates. The crust is weak. You can break styrofoam with your hands, right? You can't break metal with your hands. You can't take a sheet of metal and just break it. Well, this is aluminum, but aluminum is not a true metal. So, you can break styrofoam. Crust is weak, brittle. How do you break something? You need force. What's the force? It's convection currents in the mantle. So these convection currents in the mantle break weak points in the crust, and then it moves the crust all around on the surface of the Earth, and when plates collide with each other, they create earthquakes. That's why I tell you to look at the map for number 6. Fun fact 6. It's not a DNA, just a fun fact. First Wii Sports was fun. You guys still stuck with 12 and 13? I don't know about that. Bowling's pretty good. $1,500 was pro level, right, Logan? Can't remember. Sounds like a fun Friday night. $1,000 is pro level. Okay. Yeah, tennis was good too. I like tennis, bowling. Basketball was kind of lame. I don't remember if that was the first or the second one. Beast at the sword fighting. One v1 me in baseball. Alright guys, if you have questions throughout the day, let me know. Document whole thing is due before midnight. Okay. Tomorrow there is no Mighty Meetup. Most of the month of June will be a Mighty Meetup. Also be time for you to revise or get things done if you haven't done so. Those of you in the chat, you're probably already all set. So it'll be hopefully a relaxing transition to high school. Alright? Oh yeah, locker time today. Before you guys go, and those of you who watch, you gotta pick up your stuff at the school. if you left it behind on March 13th. Alright? Okay. Have a good Thursday. Maybe a stream on Tuesday. We'll see what's going to happen. Alright? Assuming the school sends you an email about work. Alright? You have nothing in there? Perfect. Mr. Lucian said we were the best team in terms of not leaving junk. Have a good Thursday. ACT Lab tomorrow. You still gotta sign in for attendance. Monday, no attendance. It is a teacher PD day. Teachers planning, grading, meeting each other. Alright. Bye, Hike. Bye, Azra. Bye, Rainy. For those of you who are responsible, yes,